and welcome to Alpha Omega training videos. In this video, we are going to carry out a simulation of the sloshing of a tanker truck using Ansys Fluent software. After that, we will extract some graphical results relevant to the parameters available in the solution. Stay with us. At first, open your Ansys Fluent software from the Start menu bar, and as you see, the Fluent Launcher window will be opened. Here, by hitting the read option, I will import my case file into the Ansys Fluent. Okay, here you can see the dimension of the solution, which is 2-dimensional. Solver option is selected as double precision. This option in Ansys Fluent is a computational setting that allows for more accurate numerical calculations. This option uses 64 bits to represent numbers compared to the 32 bits used in single precision. Also, under the parallel, we can see the solver processes option, which is selected as 12. This is a feature that allows you to control the number of processes used for the software. After hitting the start, the Ansys Fluent software will be loaded in a few moments. Okay, the software is loaded, and here the user window 1 is the graphical window. So by hitting the display mesh option, we can display our geometry and mesh file here. Here, as you can see, our geometry is a rectangular shape with a structured meshing. Here you can select and deselect each of your boundary conditions which is desired for you. For example, here I enter the interior, wall mesh, the water mesh, and air mesh. Okay, so this section, the green zone, is for the water, and this one is for the air. By zooming in, you can also take a look at the elements of this solution. After that, you can also check your mesh file by clicking on the mesh check under the mesh in the general section. And here you can see the work done in the console. Make sure that the minimum volume of your mesh file is not a negative value. After that, to report the quality of the elements, you can select the report quality option. And here you can see the minimum orthogonal quality, which is 1, and the maximum aspect ratio, which is about 1.4. Alright, the aspect ratio refers to the ratio of the longest edge to the shortest edge in a cell. It's an important metric for mesh quality. Fluent can handle high aspect ratio cells, but for better accuracy, it's recommended to keep it under below 100. In case of orthogonal quality, this parameter is a measure of the cell's deviation from a perfect shape. The range is 0 to 1, where 1 represents a perfect cell. Lower values indicate poor quality, potentially leading to inaccurate results. It's crucial to maintain high orthogonal quality, preferably above 0.1. Okay, next we have the solver options. But before that, I can see that you can also, by clicking on the info and size, here you can see the total number of elements in your solution. Okay, the solver type of our project is selected as pressure based. The pressure based solver is primarily used for incompressible and mildly compressible flows. This solver uses a pressure correction method to solve the Navier-Stokes equations. The steps involved include guessing the pressure field, solving the momentum equations to obtain a velocity field, and then correcting the pressure field based on the divergence of the velocity field. The process is then iterated until a converged solution is found. This solver is efficient and suitable for a wide variety of flow problems. In case of velocity formulation, it's absolute, and also the case is dependent on time, so it's transient, and the space of solution is planar. There's no axisymmetric or axisymmetric swirl boundary condition. Okay, we have gravity. The gravity is in the y direction with the value of minus 9.81. But there's another acceleration, which is the acceleration of the car, and is defined using an expression. To define an expression, you can select this option, and here you can use the expression as it is selected. If you hit this option, you can see the expression defined. Named expressions are a powerful feature that allows users to define and manage scalar or vector expressions that can be used throughout the software. These expressions can represent mathematical equations, material properties, boundary conditions, or other quantities of interest. Named expressions are dynamically updated when the variables they depend on change, providing a robust and flexible way to control simulations. They also support a wide range of mathematical functions and operators, allowing users to create complex expressions to precisely model their systems. This feature enhances user productivity, reduces the risk of errors, and makes it easier to replicate and share work. Okay, here you can see that for this expression, if is defined. If time is less than 3 seconds, the acceleration will be 5. And after that, after this time, the acceleration is equal to 0. Here you can see the functions, different functions you can use, variables relevant to different parameters, constraints, report definitions, which will be defined in this section, and also locations, cell zones, and boundary zone and surfaces. Ansys Fluent is a powerful tool for computational fluid dynamics or CFD modeling. It offers a wide range of models to simulate different aspects of fluid dynamics problems. For instance, its turbulence models are designed to capture the chaotic motion of fluids. If you're dealing with thermal analysis, Fluent offers heat transfer models. Multiphase models, on the other hand, enable you to simulate scenarios where different phases of matter interact. Fluent's combustion models are at your service if you need to simulate combustion. Finally, Fluent's species transport models enable you to simulate scenarios where different chemical species are transported by the fluid. All in all, Fluent models are designed to help you simulate complex fluid dynamics problems with ease and accuracy. Okay, here in this project we have used the multi-phase model. By double clicking on it, the multi-phase model window will be opened. Here under the models, we have selected the volume of fluid. The volume of fluid or VOF model is a multi-phase model used to simulate two or more immiscible fluids by solving a single set of momentum equations and tracking the volume fraction of each of the fluids throughout the domain. The model is typically used for the simulation of free surface flows such as waves, droplets, and dam break scenarios. It is capable of handling high density ratios, making it suitable for a wide range of applications, including the simulation of gas liquid and liquid liquid flows. After that, we have the implicit body force option under the body force formulation. This option is used to improve the convergence rate of the solution in cases where body forces like gravity or electromagnetic forces are significant. This option is particularly useful when dealing with large body forces or when the body force direction changes abruptly. When this option is enabled, the software implicitly includes the effects of body forces in the pressure-velocity coupling equations, which can lead to more stable and accurate solutions. Next to this option, we have the volume fraction parameters. The formulation could be explicit or implicit. The volume fraction parameters can be set using either implicit or explicit formulation. The implicit method solves the equations for all variables simultaneously, which makes it more stable and capable of handling larger time steps, but it requires more computational resources. On the other hand, the explicit method solves the equations for each variable sequentially, which is less stable and requires smaller time steps, but it uses less computational resources. Also, we have the interface modeling type, which is selected as sharp. Sharp interface modeling is a numerical method that allows for a more accurate representation of the interface between two or more immiscible fluids. This option enhances the accuracy of capturing the interface between phases by employing a geometry reconstruction scheme. It is particularly beneficial for problems where the interface between the phases is of prime importance. The sharp interface model can also account for phase change, making it useful for applications involving boiling and condensation. Next, we have the phases tab. Here we can name the different phase of the solution, which the first one is air and the second one is water, with the material of water liquid. Then we have the phase interaction. Here the surface tension coefficient between the air and water is selected as a constant value, which is 0.072. The surface tension coefficient is a key parameter that defines the magnitude of the surface tension force in multi-phase flow simulations. It is measured in Newton per meter and is used to model the effects of surface tension at the interface between two immiscible fluids. The surface tension force is essentially a balance of molecular forces that occur at the surface of a liquid, and it plays a critical role in a variety of physical phenomena, such as the formation of droplets and bubbles. In Ansys Fluent, this coefficient can be defined for each pair of phases, allowing for a detailed and accurate representation of multi-phase flow systems. Also, in the heat mass reactions, there's no mechanism enabled. After multiphase, for this project, the Visos model is used. By double clicking on it, you can see the total bunch of different options for turbulence models available in the Ansys Fluent software, which starts from investigate, laminar, one equation, models, two equation to five equations, and it still has SAS, DES, and even LES model. Okay, here we have selected the K epsilon and realizable model. This model offers an improvement over the standard K epsilon model by providing superior performance for flows involving rotation, boundary layers under strong adverse pressure gradients, suppression, and or circulation. The realizable K epsilon model is based on the transport equations for the turbulence kinetic energy, or K, and its dissipation rate, or epsilon. The term realizable means that the model satisfies certain mathematical constraints under Reynolds stresses consistent with the physics of turbulence. The benefits of using this model include its robustness, economy, and reasonable accuracy for a wide range of turbulent flows. Okay, that's it for the models. Here I close it. And the next section is materials. Within Ansys Fluent, the materials section offers a robust tool to manage the physical and chemical properties of materials utilized in your simulation. Think of it as a spell book for wizards brimming with possibilities. This functionality empowers you to effortlessly create, modify, and remove materials, as well as define the characteristics of fluids, solids, and mixtures. It's a valuable resource for anyone seeking to refine their simulation by adjusting the material employed. Here, the water, liquid, and air are selected or defined for the fluid materials. To take a look at water liquid, you can double click on it. Here, its name, then the chemical formula, and here the properties of the material, density and viscosity. If you want to define a new material, you can change the name, the chemical formula, or the properties of the material. Or even you can use the database of the Ansys Fluent software by clicking on the Fluent database. Here you can see a bunch of material just predefined in the library of the software. Here you can change the material type from fluid to solid, and now you can see the solid materials and you can use them. Okay, for the solution we have used the water, liquid, and air. After that we have the cell zone conditions. In the cell zone conditions we can modify the property of the zones available in our solution. As you can see here, we have the air mesh zone and water mesh zone. Here we can apply the frame motion or mesh motion method for them to give them a translational movement or rotational movement. Or even we can apply porous zone, laminar zone, or even source term and fixed values to the different zones. Okay, then we have the boundary conditions, important section of the software. Okay, here by clicking on this option and zone type, I can uh, classify the boundary conditions based on their type. Here, as you can see, there is no inlet and outlet boundary condition. We have internals. Here, by opening the internal in the outline view tab, we can right click on each of the boundaries and display them. This is the first boundary, interior air mesh, which is the air zone, and this is the water zone. Okay, if you open them, you can see that there is no option to modify, and that's similar for all of them. After that, we have two wall boundary conditions. Here I open the wall tab, the first boundary, the second one. Alright, if you select the first one, here you can see the options for a wall boundary condition. The wall motion is set as stationary wall, there is no motion for it, and also the shear condition is set as no slip. The phase here is mixture, you can change it to air or water. The options for the second wall boundary condition is uh, as same as the first one. Okay, here I close this section, and the first section, which is setup, is done. And in the next section, we will delve into the solution. Okay, here we are in the solution section, methods. And now you can see the various options available to modify the different methods of the solution solving. Okay, the first one is pressure velocity coupling, which is selected as simple scheme between simple, simple C, piezo, and coupled. The simple scheme is a numerical procedure used for solving the Navier-Stokes equations which describe the motion of fluid. The scheme is iterative and relies on guessing and sequentially correcting the pressure and velocity fields to achieve a converged solution. It's widely used due to its simplicity and efficiency, especially for incompressible and steady state flows. After that, we have the special discretizations for each of the equations. The first one is the discretization of the gradient, um, which is selected as least squares cell-based. This option is an approach used to calculate gradient vectors for scalar quantities in the fluid flow. The method works by minimizing the sum of the squared differences between the values of the scalar quantity at the cell centers and the values predicted by the linear approximation of the scalar quantity over the entire cell. This method offers a higher level of accuracy compared to other methods like the Green-Gauss cell-based method, especially for unstructured and non-orthogonal meshes. However, it may require more computational resources due to its complexity. For the pressure, Presto is selected. The Presto or the pressure staggering option method is a pressure interpolation scheme that is often used for flow problems where the pressure field is of particular interest. This method provides a more accurate representation of the pressure field compared to other methods such as the simple or piezo methods. Presto is especially useful for simulations involving highly swirling flows, compressible flows, and flows with large pressure gradients. It uses a staggered pressure discretization approach to maintain continuity and to avoid the checkerboard pressure pattern that can occur with collocated grids. For the momentum, second order upwind is selected, and for the turbulent kinetic and dissipation rates, it's first order upwind. The first order upwind method is the simplest and most robust discretization scheme, but it has a high numerical diffusion which can lead to inaccurate results. The second order upwind method improves upon the first order by using information from two grid points, reducing numerical diffusion and improving accuracy. Okay, here you can see that for the volume fraction, the georeconstruct discretization method is selected. This model is a special discretization method for the volume fraction of secondary phases. It's designed to improve the accuracy of interface tracking in multi-phase flows. By using geometric reconstruction of the volume fraction field, it provides a sharper and more accurate representation of the phase interface compared to standard upwind schemes, especially in complex geometries and unstructured meshes. This option is particularly applicable to free surface flows, uh, stratified flows, or flows where phase distribution is important. Okay, also for the transient formulation, the first order implicit option is selected. Then we have the controls. In the controls, you can see the under relaxation factors. The under relaxation factor, or URF, is a numerical technique used in iterative methods to control the convergence of the solution. It scales down the computed change of a variable to avoid potential divergence or oscillations in the solution process. Ansys Fluent generally uses a URF range between 0 and 1. If the value is close to 0, the solution will converge slowly, whereas a value close to 1 will converge faster, but this may cause instability if the value is too high. Okay, these are the values for the under relaxation factor of each of the equations. After that, we have the report definition. Users have the ability to generate different kinds of reports, such as surface reports. Here, right clicking and new, we can see the different options: surface reports, volume reports, and flux reports. These reports are capable of incorporating data about the flow field, including but not limited pressure, velocity, temperature, etc., for the specific boundaries or surfaces of their choice. Okay, after that, we have the monitors. In the monitors, if you open it, you can see the residuals. The residuals represent the imbalance in the solved equations and are used to assess the convergence of the solution. When uh, the solution is perfectly converged, residuals would theoretically be zero. However, in practice, due to numerical errors and approximations, residuals tend to reach a small value and then level off. Here you can see the absolute criteria of the convergence for each of the equations. You can monitor them and check the convergence of each of these equations, and also make sure that the print to console and plot options are enabled. After that, we have the initialization. Initialization defines initial conditions for the computational domain, setting the starting point for the calculation. Standard initialization sets uniform conditions, while hybrid initialization uses potential flow solutions to initialize the flow field, useful when the initial state is not well known. Here, for this solution, we want to initialize using the standard initialization. Okay, first I want to give the volume fraction of air as 1 to uh, all over the domain. So water volume fraction would be 0, the gauge pressure and velocities also are 0. Initialize, and now we can see the variation of volume fraction of water sorry, in the domain using a contour. Okay, here we can see that there is no water in the domain. So what we can do is to patch a water zone into the water zone mesh. So to do that, here I select the water in the phase, volume fraction, value 1 in the water mesh zone, patch and close. Now we can display the contour again, and here you can see the water volume fraction in this zone. Okay, before going to the run calculation section to start the simulation, we can go to the calculation activities. Here you can define the saved files during solution. For example, if you enter the number 10 here, the case and data will be auto-saved every 10 time steps. Here you have even more options. Also, you can define a contour, and here in the solution animation, you can select it, preview, and order to record after every, for example, 5 time steps. And the figure of the graphical view here in this window will be saved after every five time steps. And after the solution, you can even export an animation video file from the project. Okay, after that, after defining the uh, uh, file case and data saves and also the animations, we can go to the run calculation, and here under the number of time steps we have put 5000 with the time step size of 0.002. Also, the maximum iterations per time step is 20. The Ansys Fluent's iterative mode solves complex problems by dividing them into smaller parts and refining the solution iteratively until reaching the optimal results. It's particularly useful for nonlinear problems and provides better control and monitoring of the solution process. After that, you can hit the calculate and the solution will start to run. Okay, finally, after about 100,000 iterations, the solution is stopped. Here you can see the results of each of the equations defined in the solution. Continuity, epsilon, this is the k, and y velocity and x velocity under them. Okay, now we can extract the graphical results. Here in the surfaces, you can define a new imprint, point, line, or even plane, and different other options like isosurface and isoclip. But as our solution is 2D, there's no use of them, so we need the graphics section. Here I open the contours, and I can display the volume fraction of water in the both air mesh and water mesh zone. And now you can see the motion of water phase in this domain. You can also change the parameter from phases to, for example, pressure, static pressure. This is the variation of static pressure, and also the velocity. This is the velocity magnitude of water and also air. And in case of turbulence, you can check the turbulent kinetic energy and also turbulent intensity. Okay, but what we want to show you is to display the contours during the solution. To do that, we have saved some figures from different parameters during this time. The first is eddy viscosity, and also we have put the contour on the back of a truck. This is the variation of eddy viscosity in 4 different times. The pressure, streamlines, colored by velocity magnitude. Turbulent intensity, velocity magnitude, and the most important parameter, which is volume fraction of water liquid. At the initial time, 1.2 seconds, 4 seconds later, and 10 seconds. Okay, here you can also see the geometry of the solution and its meshing. Okay, that's it. And the solution is finished. We have investigated the motion of water liquid on a tanker, in a tanker on the truck, and after that, we have extracted the contours related to different parameters of this solution.